Okay, good morning. Good morning. So, we gained some familiarity with the use of the Lagrangian and the Euler-Lagrange equations yesterday, so let us continue with some additional examples, in particular to try and illustrate in more depth how we apply constraints and what information these constraints bring us. So this slide says an example with constraints. We will first look at it with no constraints, and then we will apply the constraints. So this is a ball rolling down a slope. So we should write the Lagrangian for this situation. The Lagrangian is kinetic energy minus potential energy. So what kinetic energy is there in the game? There's the translational kinetic energy, half mx dot squared. There's the rotational kinetic energy, which is a half I phi dot squared. And then there's a potential energy, which is just associated with the height of the ball up the slope. So that comes in as negative, so minus mg h minus x sine alpha. So yeah, as you very well know, potential energy, the definition of zero potential energy is arbitrary. So this has been defined such that when x is 0, it's at minus mgh. And then as x increases, it gets more and more. Well, you can see. Okay, so let us analyse this then. Initially, with no constraint. And what does this mean? It means that that we just have 2 degrees of freedom, which are r and phi, and that these are independent. Okay. So let us analyse. So let us apply Euler-Lagrange equation. We'll do this initially for r. Now the application of the Euler-Lagrange equation now should become quite routine, and it's very straightforward. So from I will start just to write down the result, but let us just, since it's early in the morning, let me do it one more time here. So dl by dr dot is equal to, oops, I said r, we call it x, I beg your pardon. So dl by dx dot is going to be given by mx dot. We're going to need to differentiate that with respect to time, and this will give us mx double dot, and we need also dl by dx, and that is going to give just a positive mg sine alpha. And then the Euler-Lagrange equation is d by dt of dl by dx dot is equal to dl by dx. So we have mx double dot equals mg sine alpha. So this is clear what's happening here. X double dot equals g sine alpha. So nothing else is happening apart from the ball is falling under gravity. Okay. Ball falling under gravity. So that's just the same result you'd get for a block. Some cube sliding down a frictionless block. Now what about Euler-Lagrange for phi? So again, having done it once, let me now just write down the result, but in this case it's very, very simple because L just depends on phi dot. So all we get is that phi double dot is equal to 0. Okay. So this tells us that the angular velocity phi dot is constant. And to remind you of the discussion we had yesterday, we could have actually appreciated that without doing any maths by just looking at the form of the Lagrangian and seeing that it doesn't actually depend on phi, it only depends on phi dot. This is obvious because L independent of phi, and I remind you of the jargon, that means that phi is a cyclic variable. And if that's the case, then the conjugate momentum, which is in this case the angular momentum, is constant. Okay. So anyway, phi double dot is 0, phi dot is constant, so that means that if you start the ball spinning at the top of the slope, it comes down the slope and it continues to spin at the same rate. Or if you start it at the top of the slope not spinning, the ball will just slide down the slope without spinning. Okay. So now let us impose a constraint that there is a relationship between x and phi. So x equals minus r phi. So you might be initially a bit perturbed by the minus sign, but that is just to do with how phi is defined. So you see that if I were to the key point is that this means that there's no slipping, so any revolution on the ball must be accompanied by an equivalent amount of motion up or down the slope, and the minus sign is there because you see if I were to increase phi defined like this, the ball would roll backwards up the slope. Okay, so it's in the opposite, somehow in the opposite direction to x. So sign, because of how phi is defined. Okay, so how could we make use of this constraint? So the most straightforward thing to do is that you could actually, and I won't do this directly, one could just make that substitution into the Lagrangian, and it would become just a Lagrangian with one degree of freedom. And that would give you the right result for that degree of freedom, but it would not give you all the information that we might need. Okay, so we could substrate in. So this is okay, but doesn't give us all available information. And this will become clear now when we do it by applying the constraint by the method of Lagrangian multipliers. Okay, so this was something we introduced yesterday, and we had one example. So let's look at it with this second example. So instead, use Lagrangian multipliers So let us remind ourselves what this means. It means that the Lagrangian changes to, so L changes to say something we'll call L prime. But I note on my slide I still just called it L, but just for the purposes of writing on the board, which is the previous Lagrangian, but then we add onto it some factor lambda times G, where G is the constraint equation. So here, G is x plus r phi, okay, because G equals naught gives the constraint which we want to impose. Right, so this justifies the form of this equation now. So what do we then do? Well, it's just as before. We evaluate the Euler-Lagrange equations for the generalized coordinates, but now there's not just two of them, there's a third one, because lambda should be regarded as a generalized coordinate. So now evaluate Euler-Lagrange for x, phi, and lambda. So let's do that. Firstly, x. So again, to be efficient, I hope you'll allow me just to actually write down the equation we get from the application of the Euler-Lagrange. So it's just as before, but now when we do dl by dx, we're going to pick up an extra term, which is just lambda. So what one gets is x double dot equals g sine alpha plus lambda over m. So this is this, okay, I've divided through by m, but this is just the same as we had when we did it without the constraints, but now we've got this extra term here, right? What about phi? So phi, so previously that gave us this very trivial expression that phi double dot equals 0. What do we get now? We get phi double dot is equal to lambda over I times r, and that is because again we have this additional term which is lambda r phi. So when we differentiate L with respect to phi, we get a lambda r. And then we must not forget to also evaluate the Euler-Lagrange equation for lambda itself. And this gives us that x plus r phi is equal to 0. And this, of course, is just the constraint. So the Euler-Lagrange equation applied for lambda will give you the constraint equation. Right, so let's then put all this information together. Let me just number these. 1, 2, and 3. Let me just manipulate 3. I can just put phi on one side and differentiate it twice, so I get phi double dot equals minus x double dot over r. And if I make use of 2, which also gives us phi double dot, so if I use 2, then I get minus x double dot equals lambda over I times r squared. And from 1, we have that x double dot equals g sine alpha plus lambda over m. So if we add these together, we get 0 equals g sine alpha plus lambda 1 over m plus r squared over I. Let's make that clearer. And hence we have found the value of lambda. So lambda equals minus g sine alpha over mi I plus mr squared. But initially we're not just interested in lambda, indeed we may not be interested in lambda at all, but I'll show you in a moment we should be. What we want to know is we want to get nice equations for x double dot and phi double dot. So let me just, these I can just write down. So now we have lambda. If we put that into the equation for x double dot, we find that x double dot is equal to g sine alpha mr squared over I plus mr squared. So this is the equation of motion for x, and for phi we get phi double dot is equal to minus mg r sine alpha over I plus mr squared. Okay, so these are the two equations of motion that we were, I think, interested in. So let's contemplate these for a moment and see what they tell us. And let's compare this with the trivial case which we have here. Here we are. So, yeah, so in the trivial case where we had no constraint going down, it was coming down the block in x as just under gravity. So now we have this same factor, but we have this, so we have the same term, but we have this factor after it. And this factor depends on the mass and also the moment of inertia. If it's a ball, we can, of course, we know what the moment of inertia is, so we can put that in. But I don't think we need to do this here. We just note that this factor is going to be less than 1. So x dot is going to be smaller than before. Okay? Before. So by before I mean the unconstrained case. Okay, unconstrained. So it comes down more slowly because of the spinning. Phi dot, also phi dot is now manifestly not equal to 0. So there is some acceleration in the spinning, and we note it has a minus sign, so accelerates and in the right direction. Okay, so I mean the right direction because it accelerates with a minus sign, and because of the definition of this phi, this means it's rolling down the hill rather than up the hill. Okay, so this is already a interesting result, I think you'll agree, but I want to come back to lambda and what we can learn from that. We can find it again. There she is. So maybe it went by rather quickly yesterday, but one of the important things about this approach is that we can learn about the forces of the constraint. Can learn about forces. And I say forces, it depends on the coordinate. In some cases, it might be the torques associated with the constraint. And if I just write down the generic expression, which we had this yesterday, it was that the force associated, I put this in inverted commas because it could be a torque as well, but the force associated with generalized coordinate k is equal to lambda times the derivative of this equation of constraint, so g, with respect to generalized coordinate k. Okay, so this was on the slides yesterday. I explained it, but it could have gone past. But let us see what this means here. So here, we have two generalized coordinates when we forget about the constraint. That's x and phi. So for x, we have f of x will be lambda times d by dx of this equation, which is x plus r phi. So the derivative of this with respect to x, it's trivial, right? It's just 1. So f of x will just be equal to lambda. So this is the, we just get minus mgi sine alpha over I plus mr squared. So what this is, it's the force coming from the friction on the slope which is causing the turning, and the consequence is to slow down the fall of the ball down the slope. So this slows down the fall. Okay. Now we have another we have another coordinate which is phi, so we can look at that. I know with phi that what we're going to end up with is not a force but a torque, so let me anticipate that to write T phi, and that's going to be lambda d by d phi of x plus r phi. So that's going to give me r lambda. So what we have here is just minus m r g I sine alpha over I plus mr squared. So this is the torque which the friction applies on the ball, and that's and here the minus sign is such that that corresponds to increasing the spin down the slope. So in this case, this torque speeds up the spinning. Okay. So we have learnt quite a lot from the system from this Lagrangian multipliers method. Right, now let's consider going to 3 dimensions and how we would write the Lagrangian in 3 dimensions, and we'll consider a bunch of coordinate systems. So firstly, Cartesians, and this is trivial, right? We've done this in the 1D case with x dot, but now we can easily generalize it to y dot and z dot. So for 3D Cartesians, the Lagrangian is as written. I won't waste chalk on repeating that. And then we've already shown what the Euler-Lagrange does with it. So already shown that Euler-Lagrange gives mx double dot equals minus du by dx. We showed that yesterday. So similarly, we have my double dot equals minus du dy, and mz double dot equals minus du dz. And if we wish, we can write that as in vector form. So m r double dot as a vector equals minus the grad of u. All right. So that is fine. Let's look at the case, though, we were now working in cylindrical coordinates. So I would very much hope by now in your maths you've covered a variety of possible three-dimensional coordinate systems. So I hope I can just write this down. So in cylindrical coordinates, then x is given by r cosine phi. So this means that x dot will be r dot cosine phi minus r sine phi dot. And y will be r sine phi. And so y dot will be r dot sine phi plus r cosine phi dot. And z is just z in cylindrical coordinates, and this means that z dot is equal to z dot. Profound statement. And therefore we can write the kinetic energy, which is T equals a half m x dot squared plus y dot squared plus z dot squared. We substitute in all of the above. And I'm just going to do this once for this coordinate system. So x dot squared, this will give me r dot squared cosine squared phi plus r squared sine squared phi dot squared. And then we have a cross term, which is minus 2r dot cosine phi sine phi phi dot. Yeah, there's not much more of this to go. And then we have that, so that's x dot squared. Y dot squared will be, give me again three terms, so r dot squared sine squared phi plus r squared cosine squared phi dot squared. And then the cross term will be plus 2r dot sine phi cosine phi dot. And then we shouldn't forget we also have the z dot squared. So this we have the plus z dot squared at the bottom. That's easy. But let's look at this mess here, and if I've written things out correctly, I note that this term is the same as this term, so these cross terms go. And then we have a term in r dot squared cosine squared phi, but we have r dot squared sine squared phi, and cosine squared plus sine squared is 1. And similarly for this term here and here, so we end up with that, that t is equal to a half m r dot squared plus r squared phi dot squared plus z dot squared. And the Lagrangian will be equal to this minus u, which in principle can be a function of r, phi, and z. Okay? So this is the Lagrangian in cylindrical coordinates. I hope that's okay. Just a remark to ram home this point about cyclic coordinates. So if we note that the Lagrangian, it depends on r, and then these r dots, phi dots, and z dots, but it doesn't. This kinetic term doesn't depend on phi. Now, in principle, you could dream up some weird potential where it did depend on phi, but if you are independent of phi, then so would the Lagrangian as a whole. And you know what that means. So that means that phi is cyclic, and so p phi, which is dl by d phi, dl by d phi dot, which is mr squared phi dot, is conserved. And this is, of course, angular momentum. So we made this remark earlier. So if you have this Lagrangian with a potential which doesn't depend on phi, then you would find that the angular momentum should be conserved. Okay, so we've done Cartesians, we've done cylindrical coordinates. I guess you know what's coming next, and I'm not going to waste too much board on this. So in spherical coordinates, then we have these expressions for x, y, and z, and so you can differentiate those with respect to time. And then if you substitute in, you find that t equals a half m r dot squared plus r squared theta dot squared plus r sine theta squared theta dot squared. And you'll forgive me for not showing that, but it's not very difficult. But if you put these in the square, then you're obviously going to get a whole forest of cross terms. But again, all the cross terms vanish as they did in the cylindrical case. So I'll leave that as an exercise for the student, and you're left with this very compact expression. Okay, great. So we're now equipped with expressions for the Lagrangian in a variety of coordinate systems. So let's try and do this. So I want to look at a rotating bead. Previously, we looked at a rotating bead on a wire, but when it was lying flat on the table. So now let's not let it put it flat on the table, but let's allow the wire to be at some general angle alpha, and this wire is rotating around this axis with an angular velocity omega. Okay, and though it's not stressed in this text, we're going to initially say that omega is fixed. Okay, rotating bead, and omega is a constant. Okay, so what is a good coordinate system? Well, it's the spherical coordinate system. So we go to spherical coordinates. And we have this expression for t, and I'm not going to write this out because it's just one board above. So we have this expression for t here. But we note that, what do we note? We note that here, theta is usually defined in the spherical coordinates, is actually here alpha, and alpha is fixed, so it's constant. We're not allowing that wire the inclination of that wire to move. It's a constant. So this means that phi dot is equal to 0. So that's going to immediately kill one term. And we also note that, theta dot is 0. Also, we note that phi dot is equal to omega, which is constant. Okay. So this gives us that t is then half m. The only thing which can vary is r, so we keep the r dot squared term, and then we have remaining r squared omega squared sine squared alpha. Okay, so that's that kinetic energy term written with only R allowing to vary. We need potential energy, let's say, so that comes from gravity. It depends on the inclination, so that's just mgr cosine alpha. So this is set at, it's 0 is defined to be at r equals 0. Okay. And so the Lagrangian as a whole is t minus u, and it's going to be a half m r dot squared plus r squared omega squared sine squared alpha minus mgr cosine alpha. All right. Great, so you know what comes next. We apply, we look at this and we have just a single generalized coordinate, 1 degree of freedom, and that is r. So we do Euler-Lagrange for r. Okay. Again, that's a manipulation which should be sufficiently familiar to you now that I hope I can just write down the expression this gives you. So this gives, well, okay, let me just, for old time's sake, let me just do that explicitly. So dl by dr dot is going to give me m r dot. And so this differentiated with respect to time is going to give me m r double dot, and dl by dr is going to give me m r omega squared sine squared alpha minus mg cosine alpha. So we put these together in the Euler-Lagrange equation and we get that r double dot minus r omega squared sine squared alpha equals minus g cosine alpha. So this is the equation of motion for the bead in R. Okay. So this is I mean, we could stop there, but let's go a little bit further. We can try and solve this. So this is a second order differential equation. Order, and it's inhomogeneous because the right hand side is non-zero. So the solution is firstly we solve the homogeneous equation, i.e. with the right hand side equal to 0. And what would we get there? Then you would get just r double dot equals r omega squared sine squared alpha, and that's like the equation we looked at yesterday. The solutions are exponential, so this would give me r equals a e to the minus lambda t plus b e to the plus lambda t. This lambda is not a constraint. This lambda is just omega sine alpha, right? But then we also need to work out the particular integral, which is some solution for r which trivially satisfies that, and the particular integral that we get is that r naught, let me call this r naught, this solution. This is just g cosine alpha over omega squared sine squared alpha. So you see it's a constant in the sense it doesn't depend at all on t. So the total solution is are these added together. R equals a e A e to the minus lambda t plus b e to the plus lambda t plus r naught. Let me just write that as r naught. And let me just apply some initial conditions to find solutions for A and B. So if it starts at rest, so if r dot equals 0 at t equals 0 and r equals, say, r1 at t equals 0, then this tells us that A is the same as B, and it's a half r1 minus r0. I'll let you show that. And then we get that r is r1 minus r0 cosh lambda t plus r0. Okay. So exactly what's going on depends on what the value of depends on what the value of things might be, but we see that so one case is that so if r double dot equals 0, then r is just the same as r0, which would take on this, and you just get a circular motion. What's also interesting to do is to consider the case where alpha is 90 degrees, and then it's lying in the plane. So, and this you should remember, I think it was yesterday, we looked at the bead on a wire lying on a horizontal plane, and that's when we already had a result there of cosh omega t. So if alpha equals 90 degrees, then horizontal, and we will recover yesterday's flat wire on a flat plane result. So we recover yesterday's bead on flat wire result. Okay. Now I want to look at one other case, which is which is putting a bead on a rotating hoop. Okay, so this is a hoop which is there, and the hoop is spinning, and the bead can move on this hoop. So the consequence is that the bead is constrained in R, so R won't be varying in this case, but phi will certainly be, well, theta can certainly vary. The bead can go up and down the hoop. Initially, we're going to say again that the angular velocity omega is constant, so phi dot is constant. So once more, this will give us a single generalized coordinate, which in this case is theta. Okay, so let us write down the Lagrangian here. So we start, as before, with, if I concentrate on the kinetic energy term, T equals a half m r dot squared plus r squared theta dot phi dot squared plus r sine phi, sine theta all squared, hang on, I've got a mistake here, phi dot squared, let me fix it and then I'll explain. I beg your pardon. Let's try and be clear. So this is just writing down the kinetic energy before half mr dot squared. The second term, it's a bit of a mess, but that's r squared theta dot squared, okay? Not as I first wrote it. And the last term is r sine theta all squared phi dot squared. But here we have that r dot is equal to 0 because the radius cannot increase, and phi dot is omega. So we end up with t is half m r squared theta dot squared plus r sine theta squared omega squared. We need the potential energy. That's, I think, just the same, not really any different from before. So U is minus mg r cosine theta. Again, we are at liberty to define the origin of this wherever we want. So here, you see this vanishes when theta is at 90 degrees. At 90 degrees, so above 90 degrees it will be positive, below 90 degrees it will be negative. And we just clearly have one single generalized coordinate theta. Right, so we can evaluate Euler-Lagrange for theta. This is the last slide. So Euler-Lagrange for theta, and I think by now you really should be willing to allow me to write down just the result, and the result is that theta double dot is equal to sine theta cosine theta omega squared minus g over r sine theta. And just to make this more compact, I'm going to define a variable omega naught squared, which will allow me to write theta double dot plus omega naught squared minus omega squared cosine theta of all of sine theta equals 0, where this omega naught squared I've introduced is just g over r. So this is the equation of motion for the bead on the hoop when the angular velocity is constant. We won't solve this in its fully general case. We'll just look at this and note some interesting, obvious special cases. So one special case is that, well, if omega would be equal to 0, then this term would go, and we get theta double dot equals omega squared sine theta, and that's just simple harmonic motion. So if omega equals 0, then we get theta double dot plus omega naught squared sine theta equals 0. And this is a simple harmonic motion. It's just a pendulum, okay? And this makes sense, right? Because if you didn't spin the hoop, you just could imagine this ball serenely rocking backwards and forwards. So if omega doesn't equal 0, let's not consider completely general case, but let's note some equilibrium. Let's note some solutions where it is in equilibrium. Okay. So that's when theta double dot is equal to 0. So it's in. Let's look for the equilibrium solution, which is theta double dot is equal to 0. And one case where this happens would be, okay, one way to get this to happen is to get this sine theta to be 0, and we can do that by setting theta either to 0 or to pi. Okay, so theta equals 0, so this is clearly an equilibrium position, a very boring solution where you just put the ball right at the bottom, then you can spin this as fast as you like and it will stay at the bottom. And then, so this is a stable equilibrium. And then there's the case where theta is pi, which is a lot more daring, where you were to put it right at the top. And again, that would be stable, but it would be a very delicate equilibrium. It would be an unstable equilibrium. Any small deviation from this and it would fall down. But there's another way to get theta dot equal to 0, and that's if you make the what's in this bracket itself vanish. So the other solution would be if you set cosine theta to omega naught squared over omega squared, which is g over omega squared r. Okay, and that's I beg your pardon, that's all written there. So that is again, this is also stable, and this is then you get to there's a single point you can set this ball where it would then just spin around in a circle. But that angle is defined, it depends on g, r, and omega squared. And of course, there will be some values of those three coordinates, those three parameters, such that this cannot be satisfied. But in general, you can find a solution. Okay, so that's enough for this week. We will continue. Next week, we may be able to finish things in just 2 lectures, and they will be on Monday. So I'll see you on Monday morning. Goodbye.